All right, so these are parallel because they told us that this is a parallelogram. So this is a definition of a parallelogram. We know that these two angles are congruent that we just marked because of alternating interior angles. And now we're moving on, and they're telling us that WX is congruent to YZ. So let's look at that in our picture. WX is congruent to YZ, and that is true because that is a property of a parallelogram. So I'm going to mark that down here. WY is congruent to WY. If I look up here at my picture, of course it's congruent because that's the reflexive property right there. So that's the reflexive property of congruence. And so now we have enough information to prove that the two triangles are congruent. So WXY, which is this triangle right here, WXY is congruent to the other triangle because we have two sides that are congruent, two corresponding sides that are congruent, and the angles in between them. So that's going to be side, angle, side, triangle congruence. That's a postulate. And once we prove that the two triangles are congruent, anything about them is going to be congruent. So we're trying to prove that these angles here, these opposing angles, opposite angles, are congruent. They have to be congruent because we've already established that the two triangles are congruent. So it follows that every single part of the triangles are also congruent. Corresponding parts are congruent. And that's it. That's the proof. Alright, so pretty straightforward stuff. Let's go down here to number 2. Here we have a multi-select. Remember that there's always going to be more than one less than all. They tell us ABCD is a parallelogram, the diagonals intersect at point W, and they want us to just figure out anything that's true. Alright, so because they told us this is a parallelogram, I'm going to go ahead and mark a few things. I'm going to mark that these are parallel, because that's true by definition. I'm going to mark that the diagonals are bisected, because that's true by definition. Or it's a property of a parallelogram, I should say. Alright, so, and we know that the opposing angles are also congruent. So let's see here. So the diagonals are perpendicular. That is not necessarily true. That's a property of a kite or a rhombus or a square. So if they told us that this thing was either a kite, a rhombus, or a square, we would automatically know that, but we don't here. DW is congruent to WB. DW is congruent to WB. Yes, that's true because the diagonals are bisected. Triangle AWD is congruent to triangle CWB. That is true as well. And you can take your pick as to how to prove it. These would be vertical angles, so this could be side angle side congruence. These sides are congruent because this is a parallelogram. So you could prove it by side angle side, but either way, that's going to be true. Variety of ways to prove that. AD is congruent to DC. AD is congruent to DC. That's not necessarily true unless you have either a rhombus or a square, which this certainly could be, but it's not guaranteed. And then W is the midpoint of AC. Yes, because it's divided into two equal parts. So this point would be directly in between A and C. So that is also true. Okay? So we got 3 of our answer choices that are true, just knowing that ABCD is a parallelogram. Moving on to number 3. They want us to show that all the triangles in rhombus ABCD are congruent. So the first thing I'm going to point out, because they said this is a rhombus, this is a right angle, and all of these angles are right angles. The other thing that we know if this is a rhombus is that all of these sides are congruent. And because all rhombuses are parallelograms, the diagonals are going to be bisected. I don't know if this is the same length as this, so I'm going to mark it as with a different number of tick marks. Here we go. All right. And that's enough. That's enough to show that the triangles are congruent. So just with the few marking a few things here, just using the fact that it's a rhombus, the diagonals are perpendicular, and that the diagonals are bisected. We have all kinds of different ways to prove that these four triangles are congruent. First of all four of them are right triangles, and they all have a side and a hypotenuse that are of the same length. So that means, meaning a leg and a hypotenuse that are of the same length. So that means that they're all congruent by HL. Alright, all four triangles are congruent by HL. Also, because we have all of the sides of all four triangles marked, you could prove that these are congruent by side, side, side. Or you can prove that they're congruent by side, angle, side, if you just look at the legs. Because angles are bisected in a rhombus, and because their opposite angles are congruent, all of these angles are congruent. So you could do angle, angle, side, side, angle, side, angle, side, angle. You could really do any of the triangle congruence postulates to prove that these four triangles are congruent just by knowing it's a rhombus. So regardless, if it's a rhombus, all four triangles are congruent, and you can use any of those postulates to do it. Just depends on what's given. Okay. Let's look at number 4. Let's skip 4. I'm going to go to 5. 5's a little easier. We'll come back to 4. So, given one piece of information about a quadrilateral, which would be enough to determine that it's a rhombus? So we just talked about a rhombus. So let's keep that in mind when we're looking at which one of these pieces individually could prove that something is a rhombus. First of all, anytime they give you the coordinates of the vertices, you automatically have side lengths, and you can use the distance formula to figure out if all of the lengths are congruent. So that would be enough to determine if it's a rhombus, yes or no. The length of each side is even better. If they tell you the length of each side, then you can easily determine if it is a rhombus based on its definition. The measure of each of the interior angles could tell you that it is a rectangle or a square, but not necessarily a rhombus, so that's not going to get it done. It could tell you it's parallelogram, but not a rhombus. Well, it could only tell you if it's a parallelogram or a rectangle here, so that's all we could do. We would know if it's a rectangle if they're all 90 degrees, and we would know that it's a parallelogram if opposite angles were congruent, but it wouldn't be enough to tell it's a rhombus. Two pairs of opposite sides that are parallel, again, that would only be enough to tell us it's a parallelogram, not necessarily a rhombus, so that's not enough information. If they told us it's a square, yes, because all squares are rhombuses based on the family tree. And the diagonals meet at a 90-degree angle, that would not be enough information, because the only thing that we would know for certain is that it was a kite, not necessarily a rhombus. So it would definitely be a kite, but it would not necessarily be a rhombus. So for number 5, the only answer choices that are guaranteed to result in a rhombus is A, B, and E. For number 4, this one's another weird one. I don't really like it, but it is what it is. Given this information, what additional piece of information would guarantee that ABCD is a rhombus? So, what do they give us? They give us that AB is parallel to CD, and they give us that BC is congruent to CD. Right? Now this one's tricky. There's not enough information, first of all, and the last option is given. Alright, we know that these two angles are supplementary because these two lines are parallel and this third line acts as a transversal. So the last two choices are automatically eliminated. AD is congruent to BC is a very convincing answer. However, because they don't tell you anything about the angles, just because this side's congruent, you could actually draw this side over here and have it be the same length, and then you don't have a rhombus, you have a trapezoid. So A, it could be a trapezoid still. So the only one that makes any sense is if AD is parallel to BC. So if you know for a fact that two consecutive sides are the same size and that the opposite sides are also parallel, the only shape it could be would be a rhombus. All right, so B is the correct answer here. It's a very confusing problem. I don't really like it, but there you have it. All right, so page 1 is almost done. You got a proof and another coordinate geometry problem. So let's get this one done as quick as possible here. So here's another proof. Keep in mind that given will always be the first reason. The given statement will always be the first one or two statements. And what you're trying to prove will always be the last statement. And prove is never a reason. All right. So AB is parallel to CD, and AB is congruent to CD, right? So they're giving us two pieces of information about the same sides of our parallelogram. Angle ABD is congruent to CDB. So ABD, remember the middle letter is the vertex, is congruent to CDB. And we've seen that many times over. That's alternate interior angles. I forgot to put given. BD is congruent to BD. That is the reflexive property of congruence. And we have enough information to now determine that these two triangles are congruent using side angle side. And if you look at our picture up here, they're trying to say that ABD, which is this triangle right here, is congruent to this triangle. So ABD is congruent to CDB because corresponding sides are congruent. So two corresponding sides are congruent and the angle in between them is congruent. So that's side, angle, side, side, angle, side on both of those triangles. So everything about these two triangles is now the same, which means that AD is congruent to BC. And because opposite sides of this figure are congruent, we know that it's a parallelogram because that is a property of parallelograms. If opposite sides are congruent, they have to be parallel to each other. So it's parallelogram. All right, so there's that proof right there. All right, so that's it for the first page. And the last question that we have to do is another coordinate geometry question. So let's go ahead and finish that up and we'll be done with our review. All right, so we have ABCD has vertices and they give us two other vertices here. So ABCD is at -7, -2, 1, -2, 1, -8, and at -7, -8. So this is a rectangle. It's a rectangle. And GHK is a similar rectangle, and they give us 2 points, 2, 5, and 6, 5, right there. And they want us to know, where J and K could possibly be located. So it's very important to note that they give us a similarity statement here. So they say that GHJK is similar to A, B, C, D. So it's important to note that GH corresponds to AB. So whatever the length of AB is with respect to GH, BC has to be the same distance. So for the other side, the consecutive side here, or corresponding side I should say, it has to have the same It has to be in the same ratio. They have to be proportional, is what I'm trying to say. So AB is 1, 2, 3, 4, 5, 6, 7, 8 units in length. And if you compare that to GH, GH is 1, 2, 3, 4 units in length. So this side of the rectangle is half of this. So if these shapes are going to be similar, then it would follow that HJ would be half the length of BC. And BC has a length of 1, 2, 3, 4, 5, 6. So this has to be 3 units in length. So possible coordinates for J and K could be 4, 2 and 2, 2. Another possibility for these two coordinates would be if they were up here, and this was J and this was K. All right, so that's another possibility of the coordinates, but they only want one example there. So the important thing that you have to pull out of this is that because these shapes are similar, their sides have to be proportional to each other. And that's it. That is it for our Unit 6 review. Make sure that you look over all your notes. Probably the most important thing for you guys to know is all the properties. So make sure that you study your table. And that's it. Good luck on your test.